Continuing along, second order reactions. Let's do it. Okay, so once again, we're going to look at this as a generic example, at least to start. And then actually I was able to find a nice example from the book here that I've included. But if we start here with our generic example, our 2A goes to products, okay? That would be our simplest example of a second order reaction. It involves two molecules, okay? Second order, it involves two molecules. And of course, that's only if this is an elementary step, meaning we recognize that the products might go on to do other things, maybe continue to react. But for this simple elementary step, if it involves two molecules, it's a second order reaction. And we could think of that as simply as we've got an A plus an A, and that goes on to form products. And from our previous example, we recognize that when there was one A going on to form products, it was first order. Well, now we have two A's. So we have first order in one, first order in the other, second order overall. Okay, we could also come up with an example that goes A plus B makes products, which would be far more representative of the way we think of chemistry, right? One reactant reacts with a completely different reactant, makes a new product. And this would also be a second order reaction. As it turns out, this A plus B case, as simple as it looks, gets crazy complicated with the math. So just for this class, because this is an introduction to kinetics, we're really only going to talk about the A plus A case as far as the rate law and the integrated rate law. But we still need to recognize that either one of these situations could be a second order reaction. Okay, an A reacting with itself or an A reacting with a B. And we should really recognize this is different than this example of just one A going on to form products. This example of just one A going on to form products means that perhaps whatever this molecule is, it's unstable and it just falls apart by itself. Okay? That's very different than this A being able to react with another A and going on to form products. I know that seems complicated to work out how that's different. It's very subtle, but it is different. Okay. So if we look at the differential rate law, or just our regular old rate law for second order, we can now say rate equals negative delta A over delta T, and that's K times A squared. Of course, if we had this other reaction, I'll just say that could be K times A times B, and that would still give us our second order reaction. Okay. So now if we were to do some calculus and integrate this thing, this is the equation that we would get. And of course, doing algebraic manipulation to get this in the form of a line. So we can see now this is going to be our y equals positive mx plus b. And what we would see here is that it turns out for the second order reactions, if you go 1 over concentration on the y-axis, you get a straight line where now the y-intercept is 1 over the initial concentration, and the slope is still the rate constant, which is very cool. Okay. And so what this is showing you here is, if suppose you weren't sure if it was supposed to be a second order or a first order reaction, well, then the ultimate test for that is you take the natural log of concentration versus 1 over time. And if it gives you a straight line, it has to be first order. But if it doesn't give you a straight line, as in this example, can't be second order. Okay, this can't be second order. Or wait, I said that backwards. I said that completely backwards. It can't be first order because we recognize if we took the natural log of concentration versus time and got a straight line out of it, then it's a first order reaction, which is what I showed you right here. But if we take the natural log of concentration versus time, and it's got some curvature to it, we can automatically rule out, can't be a first order reaction. So our next step would be to take 1 over concentration, plot it versus time. And as you can see, it ends up being a positive slope. But all the same, if we got this positive linear slope, that would tell us it's a second order reaction. And the reason why this is increasing is because we have to remember that's 1 over concentration. So in this case, for this example, when 2 NO2s react, so when one NO2 reacts with another NO2, right, collide, go on and do a reaction, the NO2 concentration is decreasing. It looks like it's increasing, but remember, it's because it's 1 over concentration. All right, so what about our units? Well, now it's a little bit more complicated working out our units. Okay, so let's work through that. So if I do some algebra here, and I can figure out the units from either one of these equations, from the integrated or the differential rate law. Either one, the units will work out. So I'm going to use the differential rate law because I think it's a little bit easier. So we know the rate is always going to be in molarity per second, okay? If time is in seconds, and we'll just keep time in seconds, okay? So then that equals K. We've got to figure out what those units are. And then, of course, it would be A in units of molarity squared. So now if we just divide this whole thing by molarity squared, so that's going to be molarity per second divided by molarity squared, that equals the units of our rate constant. And hopefully what you can see is that molarity cancels with one of those molarities. So our second order rate constant is 1 over seconds times molarity, which is, again, it's kind of a weird unit. But that rate constant is the proportionality constant that gives us the dependence of rate on concentration, okay? And of course, if we wanted our time to be in hours, we could say 1 over hour molarity. If we wanted it to be in years, we could say 1 over year molarity, just depending on how fast or slow our reaction is. So continuing along, so we can also come up with a half-life for a second order reaction. And this is the equation for it, 1 over K times A initial. So to get that, of course, we need the rate constant and the initial concentration. And this is different than a first order reaction because we will only get 2 half-lives in a second order reaction, right? 1/2, 50% reacts, 1/2, 50% reacts. And that's because it's not this exponential decay, all right? So there's another type of reaction that I want to talk about that kind of falls somewhere between this first and second order, and that is called a pseudo first order reaction, where pseudo, the simplest definition I can give you for that word is that it means like kind of a first order reaction, okay? So here I've got my generic reaction, A plus B goes to products, and when we first inspect this, we might be thinking, oh, this looks like it's going to be a second order reaction because there's 1A and 1B, 1 plus 1 makes 2. So if the initial concentrations are fairly close to each other, so they don't have to be perfectly equal, they could be, but what we want is the concentrations to be close, in the same ballpark, okay? Then this will proceed as a second order reaction. And then we could say, then we could say rate equals K times A times B. They would be first order in A, first order in B, second order overall. So, but what if one of those reactants is much less than the other? And for this generic example, it doesn't matter which one it is, okay? So what we have going on here is a limiting reagent situation, which we recognize is quite common to have in chemistry, okay? So if we have a limiting reagent situation, so in this case, I've said B is much, much greater than A. After all of that A has reacted, there's likely still going to be about the same amount of B, right? Think about this. This is just kind of like our 5% rule in equilibrium. If one thing is in huge excess, then it's not going to matter that much for the concentration. So in other words, what we can say now is any concentration B at time t is just always going to approximately equal B0. So in other words, the concentration of B is a constant. It's not really going to change if it's in large excess. And so now if we were writing this rate law, rate equals K times A times B, and I'll write times B initial, then what we're going to see here is we could lump this in to a new constant. So I'm going to call this K prime times A, where K prime equals K times B initial. And this is what we would call a pseudo first order reaction. So this would be my observed rate law. It would look like a first order reaction, even though there's two reactants involved. And again, that's because we have this limiting reagent situation going on. And so now what this means is this K would be a second order rate constant, and this K prime would be a first order rate constant. So if we were to go and do this experiment in this pseudo first order situation, we would be measuring the first order rate constant because our reaction would look like a first order rate constant. Okay? But with knowledge of the initial B concentration, we could then get the second order rate constant. And this is why pseudo first order is done. It's another way of determining reaction orders and rate constants. So you could imagine we could do a clever experiment where we make one of these things a limiting reagent, and so the other is a fairly constant concentration. We go and do the experiment, we measure the rate constant. But then to confirm that this is, what we expect to see, we switch the limiting reagent, right? We switch one with the other. We switch the one that was in excess, now that one is limiting, okay? And we should see the same rate constant under that situation. So that would give us a confirmation of not only that it's a second order reaction, but we could calculate the second order rate constant in a much more straightforward way by doing this as a pseudo first order. Okay, so this is quite common in chemistry to do this pseudo first order reaction. Okay, so the last specific type of reaction order I'll describe in the next video will be zero order reactions.